DeHority from Perimeter will give his second lecture on Orientifold lines and CoHA modules. Okay, please, Sam.
Great. Yeah, thank you so much for your attention to this talk. And we're going to continue along today on the same subject, although the discussion today is going to be entirely mathematical. There's not really going to be much more physics intuition. We're going to talk about the basics, the foundations of cohomological Hall algebras, vertex coalgebras, so the uh, generalization of coalgebras that arise in this context, and a convenient framework for studying them, and then how Orientifold lines, or the modules for cohomological Hall algebras we're going to use to model Orientifold lines, sort of fit into this framework. So we'll talk about the sort of slightly more understood stuff first as background in order to understand the new details of the construction. So what's the setup? It's pretty general. We're not going to work for this lecture in the greatest possible generality or the generality in which it's written, but we're going to like cover the simplest case, and where it's easiest to state and there's the fewest technical details. But in general, there's some features that always happen. You have an abelian category, a moduli stack of objects in that abelian category. In general, this is some horrible derived stack. We're going to impose restrictions in order to actually get a nice algebra. And then we have some cohomology theory, which slightly differs depending on context. And our sort of main restriction or our main example is going to be so that we can actually just choose, ordinary cohomology, and ignore some of the cohomological details. And that's the following example. So the example is when our abelian category is the category of representations of a quiver. You can also, if you want this to be representations of an algebra, it's really the representations of the path algebra of the quiver. Our quiver has a vertex set and an edge set, and we draw it as a diagram where our vertices are nodes and our edges are arrows. And a representation assigns a vector space to each node and a homomorphism to the target of each node. Then our moduli stack is just written as a quotient of a vector space. Actually, so here's a little bit of a typo already. So what's that? The vector space, well, or more precisely, it's a disjoint union of stack quotients, linear stack quotients. So for each dimension vector, which assigns a dimension to each vertex of the quiver, we get a vector space coming from the arrows. It's a direct sum over each of the arrows of just maps from the vertex at each node to the vertex. And this is the moduli having been rigidified by choosing a basis at each node. To get the actual stack defining the moduli problem, we're going to take the quotient by automorphisms that forget the choice of basis, which is a product of general linear groups of the dimension given by the dimension at each vertex. And in this case, we can actually take ordinary cohomology to be our cohomology theory. So we're going to focus entirely on this example. Relevant more geometric context, you have to do a slightly more sophisticated version of this construction. But let me mention some other examples that have been worked out. So one broad class of examples is the abelian category of coherent sheaves on a smooth projective or close enough to projective surface. So like if there's a group action which is equivariantly projective, then this also carries through. But you have to take a slightly funnier version of cohomology theory. You have to take this Borel-Moore homology theory. Another important class of examples is when our quiver comes with a potential. Um, so if we have some element of the path algebra, some function that we take up to terms that vanish upon taking a trace, um, then sorry, this is W is an element here, and then trace W is a function. Uh, so W is a potential that lives here, which gives a function trace of W, which goes from rep of Q to C. Then we can do all of the same construction in critical cohomology. And we get the critical coha of this quiver with potential. Um, this is an extremely important example because it's the local model for, in some sense, the most general class of examples, which is when we have a abelian category of coherent sheaves on a Calabi-Yau threefold. And in this case, the cohomological Hall algebra has fairly recently been given a general definition.
Okay, let's kind of, before you go into details, because kind of on the morally, how to define cohomological, depending on generalized cohomology, I mean, defined all this stuff, it's pretty natural. I mean, we knew it with Maxim many years ago. But the question is, what is really done? For example, we predicted that there should be definition of the algebra, whatever, CoHA or double CoHA, which is associated not with an abelian heart of an DG or infinity category, but with the category itself. And so, as far as I know, it's not done. And so then the moduli stack, it's still kind of, if you look at the stack of object, it's horrible, whatever, higher stack, but the definition is absent. So the question is, what's the status? I mean, these special cases, it's nice technical work, but as far as I know, I asked Kinja, and they still need a abelian category, which is strange from the point of view of stability structures. You have upper half plane and lower half plane, and you look only for the upper half plane. It's kind of not good. And I understand physicists also suffer from the absence of the whole thing. So I believe that it's kind of not technical. It's probably a fundamental question how to define CoHA, dropping the choice of a T structure. I
for
even
the
don't know whether anybody tried to do that.
So maybe I can say one thing is that the sort of main theorem that we announced in the last lecture, I think it doesn't define uh, a geometric construction starting from the uh, the full DG category in some sort of geometric thing. But the expectation, which we're not able to prove, is that the category C that we described in the last lecture with the appropriate braiding is actually itself preserved under mutation. So this sort of extra twist that goes from the um, uh, kind of
Okay,
meromorphic coproduct to the full coproduct
yeah.
um, has the properties that you would expect for um, a an algebra which
Mhm.
is preserved under changing the stability condition. So
Okay, let me ask you
expectation.
another question. This, whatever this Kinja and other people they did for coherent shifts, I don't remember. In their story, Calabi-Yau is what? compact or not necessarily compact.
Uh,
It's not visible on your slide, but it's the last line.
yeah, so
Other
they
example.
define some list of conditions, and they prove certain examples. So
But
uh
X, is it compact Calabi-Yau or non-compact? It's,
as stated, this is compact, but they also
yeah,
prove for
yeah.
uh also for local surfaces um
All right.
and curves.
And the question, if I replace coherent sheaves by another T structure, perverse coherent sheaves, can their definition kind of be applied, or whatever category which you construct in this particular case, will it include other
Yeah, it should
because
be okay for other horts. So they define their construction for an arbitrary CY3 abelian category that satisfies a relatively minimal list of assumptions. Um, and then they show that at least in this example it satisfies those assumptions. I think it should work for um and any heart that satisfies those assumptions. So you would certainly
yeah, but
expect
the question is whether it's true or not, because for there are infinitely many mutations from the T structure, which is coherent sheaves, to the one which are perverse coherent sheaves. So if something, if you do not know that your construction commutes with, I don't know, with colimits, these things seems to be minor, but modulo these minor things we knew all that many years ago. The question is kind of what's the last uh, mm, kind of what people have achieved since whatever 2010, or I forgot when we because it was, it's a question where some conceptual advances. For example, clearly that you can replace cohomology by some other. I mean, actually, we predicted the coha as an object in the, I believe, K0 of the Voivodsky category of motifs. We wrote it clearly. But the question is kind of what is proven. Because assumptions, we also can make the assumption that coha is defined and, and that's it. And then just do formal computations. But yeah, I
Can I
remember.
insert? Yeah.
Yeah.
So you were talking about the most of the constructions requiring the A to be abelian category, and in the
No,
trigonate
no, no,
category or DT
not me, me,
case.
me. We did it because we did not know. I mean, all this general stuff, it's obvious on the nose. The question is
Uh-huh.
how to prove anything. And people kind
My
of,
question is, what is the difficulty? Why people are not doing it for
yes,
non-abelian
you
category?
asking me or the speaker? Because
I'm asking
he
you.
uh,
says that it's a minor thing, like just assume that we have an abelian category so that the coha is well defined. I'm asking what?
Uh-huh.
I mean,
Uh-huh.
uh, it's kind of not an innocent thing. At least this difficulty will reappear again and again. Similarly to the definition of the coproduct, it was obvious from the very beginning that if you read the same diagram from right to left, you get a coproduct, but it's not an honest coproduct. Yeah, but the question is kind of what in what generality, for example, it can be if the maximal generality, this Kinja Park Safronov with their assumptions on the moduli stack, or it's something else. Though,
yeah, I'm not sure if this is the maximal possible general story. I feel like personally for me, you know, uh, you know, I'm happy like usually to work in the context of specific examples or quivers with potential where I sort of know that you can get the cohomological Hall algebra and this vertex coproduct. I think right. I'm it's I agree that it would be great to define the CoHA for a DG category. I think I personally can only make very limited progress. I don't I'm making no claims that like starting from some DG category I can construct a unique algebra. But
okay, yeah. Because there are some results of big generality, like starting from an arbitrary, arbitrary, maybe not quite arbitrary, maybe proper three-dimensional Calabi-Yau category, you can construct topological field theory. Now, if it's smooth, you can construct homological field theory. Then you can ask about enumerative invariance and blah, blah, blah. But as for CoHA, that story with TQFT, it's about rather Gromov-Witten, but CoHA, it's something about DT or whatever, PT invariance. And strangely enough, there is no same level of generality there. Despite, many people who know infinity category much better than I do, like Porta or Kinjo, they are working in the field, but still there is no definition. So it's kind of a bit disappointing. Yeah. All right, but anyway,
no, I agree. Yeah.
go ahead. Yeah.
So we're gonna focus on quivers, because somehow here this seems to be the some fundamental step that you have to handle if you're going to kind of handle the general case. Then what is the construction? And it does feel a little bit silly explaining this to Jan, but so we start with this correspondence of stacks, which we take the stack of short exact sequences, which maps to two copies of the stack on one side, giving the first and third term in the sequence, and on the other side it maps to the middle term. And in order to define a multiplication map, we need to be able to pull back via the map P and push forward along the map Q. In particular, in the example that we're focusing on of representations of a quiver with no potential, the map P is a smooth map, and cohomology is pullback is going to always be defined. The map Q is proper. It's actually smooth and proper. We can use Poincare duality to define a push forward, and the algebra A, which is the cohomology of the space with a product defined by P pullback, Q push forward, is called the cohomological Hall algebra of A. So what are its main properties? Let's say an associative algebra, and the structure that we're going to focus the most on is the existence of a vertex or localized coproduct. So as you mentioned, we want to define a coproduct on this same vector space by reading the diagram the wrong direction. And since the map P is just in this particular case, it's a vector bundle stack morphism. So the fibers are, quotients of vector spaces by groups. Then we know that P pullback is an isomorphism. And under this isomorphism, we just define the push forward to be cut product by the normal bundle to that map, which, because the fiber is given by the extension of the first class by the second, we invert the normal bundle of the zero section, and that gives us our inverse to P pullback. And so if we work in a localized setting where we've inverted this Euler class, we're allowed to pull back and push forward in cohomology. Then in order to connect to the theory of vertex algebras, we have one additional piece of structure, which is this variable z, which lives in a copy of the cohomology of BC star, or a point mod C star. Now, because these are objects in an abelian category, every object has a C star worth of automorphisms, which you can encode in an action of the stack BC star. And then we're going to kind of resolve our localization or our denominators in our coproduct by expanding all of the churn roots of the first term by adding an extra variable and expanding in that variable. So we have this map Act 1 star, which goes from this localized cohomology ring of the product to the ordinary cohomology ring with a new variable inserted. Then we're going to define this vertex coproduct to be the composition of the localized coproduct with this expansion and this additional variable. And the key property that this coproduct satisfies is an analog of the bialgebra identity, which depends meromorphically on this additional variable z. So let's construct a certain meromorphic braided monoidal category. This is easiest to state when our quiver is symmetric. I can explain the appropriate modification when it's not symmetric that we ended up using in the paper. But morally, it's just the same sort of construction. So what's our category? Our category is going to be modules over a certain ring. That ring is this universal ring of tautological classes, which we call lambda, or the tautological ring. What is it? It's freely generated over a ground field, which is more or less just the complex numbers, by the Turing classes of the tautological bundles. So on our moduli stack, we get a tautological bundle, one for each vertex, which is just that vector space at that node, descended by the the corresponding quotient with the natural group action on it. And in the geometric context, the tautological ring is going to have a different definition, which is defined by, again, Chern roots of some universal bundle on the moduli stack, maybe integrated over the space that we have a moduli stack of objects on.
Where the symmetricity plays a role.
Where does the symmetry? So not to define the tautological ring, the symmetricity is going to be when we want to expand this braiding in Z variables and have our terms be homogeneous. So it's a technical assumption that is like, had I not said that, I don't think it would have been obvious what was wrong. But in general, we just want to define a ring which is given by kind of cut products by all cohomology classes on all components of the moduli stack. And it's just, it's slightly more convenient to talk about expansions of coefficients if we have this symmetric case. So crucially, this ring is actually a Hopf algebra. We have a coproduct coming from taking the direct sum of tautological bundles. So if we pull back our tautological classes under taking the direct sum, the kth Chern class of a bundle V, if that bundle V is the direct sum of two other bundles, we express just in terms of the formula for the Chern class of a direct sum, namely it is the product of the total Chern roots, and you expand the relevant coefficients in terms of the Chern roots of the individual bundles. And now, what sort of properties does this ring have, or the category of modules over this ring? Well, it's a meromorphic braided category. What does this mean? This means we have a linear category together with a monoidal bifunctor. It's in this case going to be strictly associative. And then we have a family of translation functors, which is the same one that showed up in the last talk. For every complex number C, they have to, it depends algebraically on this parameter, meaning as we base change from our linear category to a transcendental field extension, it depends algebraically on the parameter. And then we also have the composition group law. That is, we translate once and another time, we translate according to the group action on C. And then we also require the existence of braiding, which is for every object V1 and V2, a isomorphism between the two ways of taking the monoidal structure, which depends meromorphically on Z. So it might not be defined for all values of that parameter.
But you said last time that in addition to these properties, which I had like 30 years ago, you have some additional structures. You do not require them now, or what?
No, those aren't going to be on this category. So the additional structures, so this twist is going to arise on a new category that we construct from this one.
Oh, okay. And another question, your lambda, is it what? It's an, I forgot. It's algebra of polynomials and finitely many variables, or what?
So algebra symmetric
I'm,
polynomial. I mean, it's
yeah.
symmetric polynomials in the Chern roots. So it's
Yeah, but it's finitely generated, yeah? Or
uh,
what?
I mean, there's an infinite number of Chern roots. So it's
If there are infinitely many non-zeros, then you should say what modules do you consider, because
uh,
nowadays you see you have options.
yeah. So right. I want there to be a appropriate grading by dimension vectors, and then for all of the dimension vectors to live in a particular cone.
Uh-huh. Yeah, but in general, they don't have to be finite dimensional, they whatever. Yeah. They
No, they're not necessarily going to be finite
okay,
dimensional.
good, good, good.
Uh, e- but for each dimension piece, then there's only going to be a finite number that's finite number of k that contribute.
Yeah, okay,
Um,
good.
great. Uh, and right, so our category modules for this ring with this tensor product, a braiding, which is given by the swap composed with this ratio of x classes, and this translation, which is given by this BC star action. Um, and then this proposition, which as you say, has a long history. So it I would say it's you know, a version of it appeared in the first cohomological whole algebra hit proof yourself with Kontsevich. The sort of localized story was formalized, again in some generality by Davison, and this vertex story, and the connection to this vertex co-algebra defined by Joyce was written down by Alyosha. Um, is that our algebra is a bi-algebra object in this meromorphic braided category. So there's a convenient language to kind of draw relevant identities and do calculations in this setup where we write objects in our category as lines, and product as a fusion of lines, coproduct as a splitting of lines, and our braiding as our two lines crossing. And then we'll write our Z variables where we need them to sort of say that this is the braiding is taking place at the value Z, which is a coordinate on this extension. And then the compatibility results that this coproduct satisfies. The first one says that we have an equivalence between these two meromorphic morphisms. So on the left, we've taken the coproduct valued at z plus w, and then on the right, evaluated at z, and then on the right, we've taken the coproduct z and then at w, and then these two meromorphic expressions agree. Which, if we take expansions, expanding around w, well, I guess it's w and z is equal to infinity, we get the association identity for a vertex algebra, but dualized. So this is dual to the identity familiar in vertex algebra language that y of a w y of z is equal to y of a w minus z. Z as rational functions up to a, yeah, I think I have to do a change of coordinates. So this is up to a change of coordinates where I think w prime is equal to z plus w. So
in the vertex algebra, there's called weak associativity. On the left-hand side is some sort of a commutator. But
yeah,
you don't need a commutator.
Right. Yeah. This is a weakly associative, and
well, this is probably something called the open string. There's a parameter you can just kill one of the term, and that becomes this. This type of thing. I believe Yi Huang also discussed this sort of associativity. Yeah. Oh, thank you. Yeah.
yeah. What did you say the name of the
Well,
relaxation?
Huang,
Victor
old
Katz and
story.
also Yi Huang also discussed. They call it open string vertex operators.
I see. Yeah, I'm familiar with this under the name of a weakly, the dual of the notion of a weakly associative vertex algebra. And right, usually when people say vertex algebra without assumptions, it's assumed to be local, and this is just in general false in this case, as we have non-local and only weakly co-associative vertex coalgebras. And and then finally we have this this second identity, which is a meromorphic version of the bialgebra identity, says that if we multiply and then co-multiply, then this is the same as having co-multiplied both factors and then multiplied. And again, we require these two terms to be the same as meromorphic morphisms in this category. Right. So all of these stories have a long history. The sort of main contribution of this project had been to find the analog of these results for Orientifold lines. The main tool that the sort of new tool that we use for this construction is taking fixed point stacks of the relative stacks under consideration. So the new data that we want, that everything is going to depend upon, is an anti-involution of our underlying category. So we want a category that has a map which is involutive on objects and reverses corresponding arrows. But we need this to be a group action on a stack, which is a little bit more data than just the anti-involution. We also need a co-cycle condition, which means we need a natural transformation from the square to the identity, which there's versions where it's required to satisfy a co-cycle condition, and then there's weak versions where there's an additional data and it's only required to satisfy up to some higher weaker homotopy. And for us, the only time you need to use the higher data is when there's a sign. And so it's safe to just think of actually a sort of strict action on the stack. Then the fixed point stack is defined by this this pullback diagram. So we have a natural map from M to BG, and the fixed point stack is defined as pullback of the space of the mapping stack from B gamma into M that are further required to with the identity map coming from the identity morphism from B gamma to itself. In completely down to terms, it's very likely that you're familiar with this construction, because all it really is an object in the category, together with an equivariant structure under the group, which means we have an isomorphism from gamma pullback of that object to itself that's required to satisfy the cocycle condition. And let's see some examples. So our main example is when our abelian category is just the category of finite dimensional vector spaces, which is this union over n greater than or equal to 0 of BGLM. Our anti-involution is the map that sends a finite dimensional vector space to its dual. And then the fixed point stack, well, we want a vector space together with an isomorphism to its dual. And in this case, and this is a great exercise to do to sort of get familiar with self-dual structures, is that the cocycle condition, if we choose our obvious natural transformation from the square of this map to the identity, our cocycle condition forces our pairing to be symmetric. So this says that our fixed point stack are finite dimensional vector spaces together with orthogonal forms. Had we chosen a different cocycle, a different way of identifying the double dual with our original vector space, then we would have gotten finite dimensional symplectic vector spaces. And then a slightly more sophisticated example is where we take the abelian category of representations of our quiver and an anti-involution on that quiver. So we want an isomorphism from the quiver to the quiver with arrows reversed. So in particular, yeah, if you have this A3 quiver, I think this is our only option. And then we define this involution sigma to be pullback along tau. We dualize all of the vector spaces to get the inverse maps. And then there's some flexibility of sign. So the most general case also multiplies by minus signs on a bunch of the arrows. And what are the fixed point stacks? Well, the fixed point stacks are representations of an orthosymplectic quiver, where the group we quotient by at each node is a general linear group, supposing our vertex lies in a orbit of size 2, and it's a symplectic or orthogonal group, depending on our choice of cocycle, if we have an orbit of length 1. And our fixed point stack is, again, a linear quotient stack. So we take the fixed points of the underlying vector space under the involution and quotient by the fixed points of the group, which is going to be a product of general linear, symplectic, and orthogonal groups. So what is our construction? How do we get CoHA modules that we're going to model Orientifold lines with? Well, we take the convolution of two of the stacks defining the CoHA multiplication. So the sort of source of our convolution is 3 copies of our moduli stack, and the target is 1 copy. And then we take fixed points under the map that exchanges the first and third factors and acts via our anti-involution and acts via the involution on the middle factor and therefore also on the last factor. And then does the only thing that you could do on the roof of the diagram to make everything compatible. We define the roof of this diagram to be short exact sequence OSP. And then the target of these diagrams are exactly these types of products. We call this the orthosymplectic extension diagram. And we can likewise define a module together with an action and a vertex or localized coaction via push-pull along these diagrams. So
I have a quick question here in this setting. When we talk about fixed points, you have a sigma acting, and you can pull. It's a functor, and the functor fixed point means that the twist of objects is isomorphic to the original one. But it depends on what isomorphism one take. And do you care about you want
it's extra
choose
data.
Isomorphism or just you quotient out the isomorphism?
So no, it's not you choose the isomorphism, so it's not a subfunctor. But there is a map. There's a forgetful map.
I see. So each time one has to choose a specific isomorphism.
Yeah, there's a choice. So for example, for vector spaces, it's not just a vector space which is isomorphic to its dual. Under some isomorphism, it's the choice of the orthogonal form.
Choice of that isomorphism.
Yeah.
Okay.
So yeah, so it's not a subfunctor.
Okay, thank you.
Yeah. So what's the sort of most straightforward example? The most straightforward example is when we take the quiver, which is just a particular point, then our extension diagram is just the classifying space of the parabolic that defines parabolic induction in some classical type. So parabolic induction comes from kind of splitting our Dynkin diagram. The general linear case comes from splitting a type A Dynkin diagram. And the classical types come from splitting classical type Dynkin diagrams. At either end, we can have a type B, type C, or type D Dynkin diagram, and we get these parabolic induction maps, and we're just doing pull push along them. Then all of the same sorts of constructions work. So our push forward functor is again defined via localization, where we take the fixed points of the vector space in the fiber modulo the corresponding fixed point group. And this has this nice description just in terms of the underlying X's in the previous category. And from this data, we can define the ambient kind of simple meromorphic module category that's our Orientifold lines are going to live in. So what is the structures that category has? Well, we're starting with a module category over an underlying category that also has an involution sigma. And it's a module category if we have a certain bifunctor from C times D to D, and a natural transformation to that this from that bifunctor to this other bifunctor where we've sort of modified one of the terms by the involution of the underlying category. So these are required to satisfy the obvious identities. And for this kappa, it's supposed to be this Chladni reflection equation with spectral parameter that we wrote down last time. And then for us, what is this category? Well, it's going to be this this version of the tautological ring, where we take the Chern classes of the tautological bundle on the fixed point stack. And there's kind of fewer classes, so you know, bundles with symplectic form or orthogonal form don't have any even Chern classes. And on the fixed point stack, we've identified one of our tautological bundles with the dual of another one if they lie in distinct orbits. So we only get bundles for the quotient of our vertices, and those that are fixed, we only get every other Chern class. How is our module structure defined? Well, it's defined via this version of the direct sum pullback. So there's a sort of classical type analog of the direct sum where we take the direct sum with an object of general linear type and its dual under our appropriate duality morphism, because V and sigma star of V have a natural identification with sigma star of each other. This defines for us a another object with a natural choice of isomorphism to its dual. And then our braiding is likewise a sort of fixed point analog of the same braiding as before. So we take the ratio of these x classes. Now it's x for the fixed points. We expand in our z variable.
A quick question in the meromorphic module category. So you have this. You also have the cohomological class Z of the point for the C star. So how does the sigma act? Does the sigma reinverts or change Z to negative Z or something?
Yeah, it sends Z to minus Z.
The negative Z. Okay. Yes.
Yeah.
Thank you.
Yeah, so it acts via the same Orientifold transformation, which is a negative parameter in that variable. And from this data, we can define new diagrams. So we're going to draw our objects in this category D as sort of thick lines. And we have now an action map, a coaction map, and this you know, reflection or you know, type BC braid group generator. And then what sort of structure does this module have? And we couldn't find in the literature exactly the you know, axiom that we ended up kind of showing was satisfied by these modules. But we noticed that it looked extremely similar to a notion that is actually quite well known. And so we defined it to be a twisted vertex Jeter-Drinfeld module in this particular category.
What is Jeter-Drinfeld module?
So that's this second axiom. So there's kind of two pieces of data. One is a funny version of being vertex coassociative. So we'll talk about the details of what this means next time. but it's somehow an Orientifold version. It took us a long time to realize what actually the physical setup was. That it's not this kind of usual notion in vertex algebra world of a twisted module, but there's a version of co-associativity, and then it satisfies this identity between the action and the coaction. So
You
this
see,
is our
I cannot differentiate the picture. So then it's identity, it's pictorial, something for algebraic identity. But the question is about this. That's I remember that when I gave this definition of meromorphic tensor category, kind of the guiding line was the notion of chiral algebra, which Bilenson and Drinfeld introduced more or less at the same time. So then in the end, it's kind of, as we discussed, so you can replace the line C by maybe more general curve, get some kind of factorization algebra structure. So this, okay, but this is just on the algebra side. Like roughly you replaced CoHA maybe by some factorization algebra, but what's on the module side? How to think geometrically? What
Yeah,
kind?
so for these modules, it's not just factorization algebras over an orbifold curve. Uh,
Mm-hmm.
we did figure out um uh, a sort of setting in this, and later realized this sort of Orientifold idea. So the basic idea is that we want to replace which in the vertex algebra story, a vertex algebra, comes from power series expansion of chiral algebra, and so we want to replace D modules on the Ron space of some space X. So this is the union over all finite sets of maps from that finite set into our space X. Sorry, that's not a disjoint union. That's a appropriate actual union. We want to replace this with uh, D modules on what uh, you can call Ron BC of X, where if X has an involution on the space, which is given by sigma, this is a union. Our union is taken over all of our diagonals. Here, our union is over, again, finite sets of xi, well, and also pairs of functions from I going to plus minus of x to the I, and now we're going to include diagonals and anti-diagonals. So
Yeah, so it's visible on the level of the run space, not on the level of the actual curve. Yeah.
right. Yeah, so on the curve itself, yeah, this is somehow and maybe the Ron space here is not so different actually from the Ron space on the orbifold, but somehow the module, rather than being, kind of sitting at the orbifold point, uh, where we take our convolution diagram kind of uses both the Ron space for the underlying curve and the BC type Ron space for that curve. And then we have some open subsets U going to the BC type Ron space for that curve. And so since these kind of funny Orientifold modules are for factorization modules that sort of live at an orbifold point of a curve, you still just have the same Ron space on both sides. Whereas here we kind of have an action of the Ron space with the folded Ron space, which seems to be the right language to describe these Orientifold constructions.
So BC stands for two different choices of square root or what? What
No,
is
it's just
BC?
it's just one. So like for while groups, they fit into like A, B, C, D, and so on. So the type B while
What
group
do you
and
mean
type C.
so on? You'll stop very quickly.
The,
If it's for type, yeah.
the
Yeah,
while
yeah,
group
I
of S
understand.
log.
It's symplectic, and yeah, that's what I
Yeah.
mean. Two different choices of square
Give
root.
you the same thing.
Yeah. Okay. And also a question, like you said that some category which you'll define and then will be invariant with respect to mutations, but so far you use just CoHA, which is one half of the actual thing which one may want if you want to have mutations which kind of, do not preserve the upper
Yeah, they
half.
don't preserve that half. No, that's correct. So the being preserved under mutations, we don't have a proof of this fact, but for that for that construction, no, you're right. We have uh the expectation which uh the yeah, maybe this is sort of different from uh what I just talked about, but the yeah, maybe I can briefly mention what um our category C is going to be. C is going to be um built from uh the category of CoHA modules. So it's the chiral center of the category of coha modules, which is a notion that we define, and it's going to in particular consist of as an object, we're going to have well, actually, if you define the notions appropriately, these are going to be vertex algebra associated to A comodules in the category of A modules. And yeah, extremely intuitively, the kind of negative half of the algebra comes from some appropriate vertex coaction coming from the action. And yeah, the hope is that we can take this category, apply some sort of Tanakian reconstruction and recover an algebra which is preserved under mutations. But we, at the current moment, we're able to define, a braided category, and you can abstractly, and we do get in certain cases a fiber functor, and you can define an algebra as endomorphisms of the fiber functor, but we don't know what the algebra is or whether it's preserved under uh, mutations to define the same sort of algebra. But the dream is to say that
Yeah. So
he's
to
preserved.
reconstruct whatever you need via Tanakian
Yeah.
construction. Yeah.
Um,
Okay. It's quite good. Yeah. All
Sorry,
right.
can I ask a question
Yeah,
to the other?
sure.
oh, hi,
Yeah,
Wenjin.
hey Sam. Yeah,
Yeah.
so
So
the
you're a co-author and you ask questions, you should to yourself. Yeah.
I just meant like so aren't classical limits of this quantum Yang-Bax equation gives me classical R matrices, and they're associated to classical, associated to Lie algebra structures. This K matrix, is there like a classical structure that it can associate it to?
Yeah, there is. Yeah, you can write down the sort of classical. So in the Yangian case, you can certainly write down a classical Chladni reflection equation. I and it's some structure. I have a really hard time having an intuitive sense of what it means. So yeah, you're right. The classical R matrix gives some sort of gives a Lie bialgebra. You can likewise write down a classical version of the Chladni reflection equation. I don't really have strong intuition for what that structure means.
Yeah, thanks.
More questions? If not, well, then tomorrow Sam will give his last lecture, but it will be, I think, a different time. It will be local time, 3:30, 4:30 on the East Coast. All right, thank you. Thanks.
Thanks.